Hello and good day everyone. My name is Alioscia Hamma and I will be presenting this work in collaboration with Davide Rattacaso and Patrizia Vitale towards the geometrization of quantum complexity and quantum chaos. Our goal is to exploit the geometry of quantum states to investigate problems in quantum dynamics. In particular, we are interested in dynamics that is generated by local Hamiltonians, because in nature all interactions are local. And this poses a great deal of constraint on the quantum states that are actually accessible in nature, because all the interactions are local. This is important in the context of defining quantum phases that are away from the equilibrium, the process of equilibration and thermalization, the onset of quantum chaos, and notions of quantum complexity. Given a family of quantum states parametrized by some coordinates lambda I, this space can be endowed by a geometric structure called Quantum Geometric Tensor, whose real part is a Riemannian tensor that gives rise to the Fubini steady metric, and where the imaginary part is the Berry's curvature. Now, I was talking about locality before, and I was saying, this gives us constraints about what are the accessible quantum states. In the mathematical formulation of quantum mechanics, all states are equal. You have Schrödinger's cats and other simpler superpositions, like superpositions between two spins 1/2 in an NMR device. But we know they're not equally accessible. Schrödinger cats, macroscopic Schrödinger cats, are very hard to observe. They may never be observed, but we do experiments at the macroscopic level where we show coherent superposition. Why is that? This is because all interactions in nature are local, so it is extremely difficult to produce a state that is macroscopically entangled, and for a similar reason, a macroscopically entangled state is also very fragile. So not all states are equal. Some are more robust than others. Those are the states that are accessible. And this is because of locality. We will see that this will play a very important role. So geometry has been used to investigate the properties of the ground state of local quantum systems. So you have a local Hamiltonian with local interactions that depends on some parameters lambda. So for every value of lambda, you get a corresponding ground state, and therefore you have a manifold of ground states. You study the geometry of this manifold of ground states of your model, and you find that the quantum geometric tensor describes very well the quantum phases, in the sense that quantum phases are domains of analyticity of the quantum geometric tensor, and quantum phase transitions are loci in which the quantum geometric tensor is non-analytic. So this is a static notion. These are the ground states of a local quantum Hamiltonian. Now, do we have a geometric description of states that are away from equilibrium, they are evolving in time? So can we give a Cauchy picture of a manifold quantum states that is evolving in time, and as it is evolving in time, it inherits a geometry? This would be very relevant to understand whether we can talk about equilibration, thermalization, complexity notions that are time-dependent notions with geometric tools. So yes, the answer is yes. That's one of the merits of our work. And the way we do that is that we start with the manifold of quantum states at the time 0. These are the ground states of local Hamiltonians parameterized by lambda. And then you define a new family of Hamiltonians, quench Hamiltonians, also parameterized by lambdas. And they are local as well. Therefore, each of these states will be, in M0, will be not an eigenstates of the quench Hamiltonian. And under that Hamiltonian, they will evolve in time, according to this picture. And now you will define a new family at the time t, for every time t, a new smooth family of quantum states. I should not say smooth, continuous family of quantum states. And the question is, do we have a quantum geometric tensor there? The answer is yes. And this is it. This is the quantum geometric tensor at the point lambda and at the time t. It's the space-time version. We studied many of the properties of this quantum geometric tensor. In particular, we know how to bound from above the eigenvalues of this object. And we also show that these eigenvalues are related to connected correlation functions between local operators that are present in the Hamiltonian. One of the questions that we ask is, okay, so if we have a quantum phase diagram at the time 0, so we have a domain on non-analyticity, and we evolve in time, can time evolution change this diagram, or it's conserved in time? It will deform it, but can it change? Can it change in a topological way what are the lines of non-analyticity? By using the exponential clustering theorem and the spreading and theorems and spreading of local correlations, we can prove that non-analyticities cannot be neither developed nor destroyed. As a result, the phase diagram is conserved in time. Moreover, we can prove that the quantum geometric tensor, although is a time-dependent quantity, will fluctuate with fluctuations that are very small. In other words, it will equilibrate in probability. This means that during the time evolution, it will take typical values. So this is the type of equilibration that is possible in a closed quantum system that is evolving unitarily in time. Another result is that we find an upper bound between the eigenvalues of the quantum geometric tensor and the time-integrated out-of-time order correlation functions between the operators that make up your local Hamiltonian. So this is a formula and that allows you to find an upper bound. The interest in this is that the out-of-time order correlation functions are the main tools nowadays to investigate questions about the onset of quantum chaotic behavior. Finally, we apply our findings to a specific model, the cluster XY quantum spin chain. This is a spin chain of spins 1/2 that has many phases. It has a very rich phase diagram where you have regions of symmetry breaking, regions that are disordered, and regions, those where the cluster term is prevailing, that are topologically ordered. We computed a quantum geometric tensor in its time evolution for all the possible parameters, and we indeed showed that all the theoretical results are confirmed. In particular, you can see that the phase diagram is conserved in time. To summarize Our main results are these 4 take-home messages. First of all, states away from equilibrium can be described and explored and understood using geometric methods. Our geometrical description is connected to the spreading and the scrambling of local correlations. And this is connected to questions of quantum chaos and quantum complexity. The phase diagram of out-of-equilibrium quantum states is robust, so it is not destroyed by the time evolution. And this phase diagram and the quantum geometric tensor that describes it equilibrates in probability in the sense that it assumes typical values. To conclude, a couple of things about outlook and perspectives. The result about, as anticipated, the result about out of time order correlation functions gives us an entrance to understanding quantum chaos with geometric tools. Out of time order correlation functions decay very fast for quantum chaotic Hamiltonians. This is a consequence of the fact that quantum chaotic Hamiltonians scramble in a very efficient way. We have seen that a certain type of out-of-time order correlation functions that are directly connected to the local interactions are an upper bound for the eigenvalues of the quantum geometric tensor. So this is something that we find very promising, that of trying to use geometric methods to understand quantum chaos. The second thing that we are thinking in perspective is that we've seen that not all quantum states are equally accessible. This is because interactions are local. Therefore, there is a cost in reaching a quantum state with the constraint of local interactions. If we didn't have this constraint, every state would be equally easy or equally difficult to be reached by a unitary operator. But with the constraint of local interactions, some are more complex than others. And we would like to understand how this is reflected in geometry. In particular, more complex quantum states would have a greater geodesic deviation from simple quantum states. So this is all. Thank you for your attention and have a good day.
So on the behalf of Michel Berthier and Florio Ciaglia, I would like to thank you for coming here, but I'd like to know if Michel and Florio would like to say something to us. Okay.
So just to thank again the people who have attended this session. I think it was quite interesting, and I thank you particularly Eduardo for chairing this session. And I'm sorry again, I couldn't be with you this morning. So thank you.